Hey guys, what's up? Thank you for your patience with all of this. So I'm glad that I did call out on Tuesday or switch to virtual, because it turns out it is COVID. So I will be back in on Tuesday, with a mask and stuff, uh, following CDC protocol and all that. If anybody has any questions or if you're nervous to be around me after I get back, let me know. Reach out personally and we'll figure something out. Even if it's just I switch you to a Wednesday class just so you get a couple extra days. I don't know, I'm thinking autoimmune type of things. But that may not be an issue. Still not feeling well, so be patient with me. Okay, so we mentioned that generally, especially in a case like this where we see like A and B are kind of in similar complementary directions is what I'll say. In that case, our longest vector is going to be our resultant vector. So in this case, if this were component vectors and a resultant vector, A and B would be our component vectors and C would be our resultant vector. In that case, the law of cosines, our law of cosines that we've talked about is r squared equals p squared plus q squared minus 2pq cosine b, where b is the angle opposite your resultant force. So in this case, if your resultant force is c, we would have c squared equals, doesn't matter which one you put first, but a squared plus b squared minus 2ab cosine e. E would be that angle opposite that c. That's the law of cosines that we go to most often in this class. However, let's say we were looking to find vector b and we did have angle d. We could have a b squared equals a squared plus c squared minus 2ac cosine d. So it doesn't have to be your resultant, but make sure your beta is what is opposite your, I guess we'll say what's on that side of the equal sign. Okay. What is the law of sines for this triangle? So the law of sines is either going to be the magnitude over the sine of the opposite angle. Law of sines is a proportion, right? So there's going to be, for a triangle, there's going to be 3 terms or 3 parts to the equation. And so it's going to be either, so I was just saying it kind of flipped, right? Because if it's a proportion, if we flip everything, it doesn't matter as long as we're consistent with what we do. So I was going to say like C over sine of E, A over sine of F, and B over sine of D. The alternate would be to do your signs on top. Kind of just to minimize error. If you put your unknown in the numerator, it's a little bit easier, but it really only will save you a step or so. Any questions? With this kind of format too, just if you have questions, interrupt. I may forget to ask. And if there are questions and I get silence, I'm just going to keep going, because I know there's a mute type of thing on this. Okay, so we talked about this on Tuesday, that if you're in equilibrium and you connected all of your forces head to tail, they would create a closed polygon, which also means that if we're not in equilibrium would be all of our forces are balanced. If we're not in equilibrium, then, and we were to connect all of the forces we have head to tail, then going from the tail of the first to the head of the last would be our resultant force. So like in this example, if P is a component force, Q is a component force, and S is a component force, R is our resultant force. You know how I was saying with this one that when our component forces are in complementary directions, their resultant force is going to be the longest. So in this case, I guess what I mean by complementary directions is like they have the same either positive X element, positive Y element, so on. In this case, we have P with a positive X, positive Y, Q with a positive X, negative Y. took a minute there, and S is going towards our third quadrant, so it's a double negative. That's why our resultant is shorter, because they're not in complementary directions or adding to each other, right? We started introducing on Tuesday as well our unit vectors. So for now, what we've talked about with unit vectors is that we have a unit vector I, which is completely along our x-axis, and a unit vector j, which is completely along our y-axis. As we go into it, I think it's actually our next week content where we're going to start creating unit vectors that are specific in the direction of our force. But for now, we're only talking about our I and our J. Resultant force, we started introducing that component, XY component method is what we call it. So with that, if you were to break every force up into its X and Y elements, and then sum the X elements, sum the Y elements, you're going to get your X resultant force, the X element of your resultant force, and the Y element of your resultant force. And then through having both of those, you can find out the magnitude and the direction of your resultant force. Okay, so this was the example that we looked at on Tuesday. You are gonna need to use some trig to separate your X and Y components, right? And so one thing that I mentioned on Tuesday as well is that in order to use these equations here, well, let's actually shrink that down. In order to use the fx equals f cosine and fy equals f sine, we need to be working with an angle that's an angle from the positive x-axis. Meaning in this case with f2, that's 20 degrees from the positive y-axis. If we wanted to use these, if we wanted to use these equations, we would have to add 90 degrees to this 20 to make it so that the angle came from this direction. At 4, we could do a negative 15. You also have the option of just using our trig that we kind of talked about, I think our first class, our SOHCAHTOA, or our, you know what I'm talking about, sine, opposite, hypotenuse, that one. So anyway, point is we're going to take all our forces. The magnitude is going to be the greatness of the force. We're going to separate it into its X and Y components using our trig. Sum the X components, sum the Y components. That gives us our resultant force in the X direction and our resultant force in the Y direction, or their X element and Y element. X component force, Y component force. You could think about it like that. And then we can use our Pythagorean theorem to get our magnitude. So the magnitude of the resultant is going to equal the square root of the sum of the squares, the X element squared plus the Y element squared. So C squared equals A squared plus B squared. C is our R, A and B are our X and our Y. Cautious with this tangent equation, because, so in this case, where our resultant force is in the first quadrant with a positive X value and a positive Y value, this works fine. We put in our numbers and it gives us an angle. It is going to give you the first quadrant angle. I don't know if that makes sense. So let's say we had instead, where is it? Let's say we had instead Rx is negative 199 and Ry was negative 14. Then our tangent would be the same equation, right? Tangent of alpha would equal negative 14 over negative 199. Those negatives double negative, so it's same positive. So we're going to get that same 4 degrees, but our 4 degrees would be from a different area, right? From a different reference line, let's say that, reference axis. Because if it's in the third quadrant, right, we would have something down here. It looks like, I think it would be there, right? This would be our 4 degrees. So make sure you specify that on a homework or a test or whatever. You can either draw a little picture saying like what angle you're talking about. Or you could add the 180 to that 4. Remember, I'm talking about if these were both negatives and we're in the 3rd quadrant. Add the 180 to it to make it an absolute. Okay. So equilibrium, when the sum of the forces in X and the sum of the forces in Y equals 0, that's when we're talking 2D. Next week we'll go to 3D and that'll add in our Z element. But we talked about free body diagrams. Right now, they're going to be a point with all the forces that are acting on it. Next week, they'll start to grow. This problem we did, so I'm going to scroll down to this one. Okay. Any questions? Cool. It is desired to determine the drag force at a given speed on a prototype sailboat hull. The model is placed in a test channel, and 3 cables are used to align its bow on the channel center line. For a given speed, the tension is, so for a given speed, what that tells us is that we are in equilibrium. Because if we were not in equilibrium, we would have some element of acceleration, right? Force equals mass times acceleration. So in order to know that it's a constant speed, that tells us that we are in equilibrium and our forces are going to balance. For given speed, the tension is 40 pounds in AB and 60 pounds in AE. Determine the drag force, and then we also have where the flow is going. So in terms of our have-need question structure, just to make sure we get the most partial credit or the most structured flow of having a structured flow of solving your problems feeds into getting the partial credit. It also will help you slow down your brain and catch more things. But anyway, what do we need? We need the drag force. So the drag force is going to oppose the flow or the direction of the movement, right? Actually, we'll say it's going to go with the flow. At a given speed, so we know equilibrium. 3 cables, so we have 3 component vectors. Having 3 component vectors means that we're not going to be able to use our triangle methods, right? Well, actually, you could in this case. No, wait, hold on. No, you cannot in this case. A model is placed in a test channel, 3 cables on the channel center line. So that tells us that the resultant is on the x-axis, is even with the x-axis. So 0 degrees, right? For a given speed, tension, so we have our 2 tension values. We do not have their directions, we just have alpha and beta. That's not true. We do have their directions, even though we do have alpha and beta. We have these dimensions to it, so 7 feet and 4 feet, so we can figure out proportionally what direction these are going in. Okay. So I'm going to start by, I like tables. It helps me keep things straight in my brain. Some students are able to do this without a table. Up to you what you feel most familiar with. But I'm just going to start putting in the things that I know. The magnitudes of my force, so I have TAB is 40 pounds, TAE is 60 pounds. We know it's an equilibrium, so our resultant is equal to 0. So there's going to be kind of 2 types of questions with our XY component method. So the first is going to be like sample problem 2.3, where it is here is a situation, determine the resultant of these forces. So in this case, the reason this one's not in equilibrium is this A this where this is bolted, it's going to balance all the forces that it's faced with. So technically, you might start hearing the dogs. Technically, when we start doing our like boundaries for our free body diagrams, usually anywhere you make a cut, you want to introduce a force. And that's going to be something that we're doing next week. In this case, we didn't, which is why this one is not in equilibrium, even though it isn't moving. I hope that makes sense. But so when we have something in equilibrium, I'm sorry, when we have something not in equilibrium, we're trying to find the resultant force, we're going to sum and get values for the resultant force. And in case like this one as well, honestly, but also this one. Since we know that it is at a constant speed, we know that the resultant force is 0. We're trying to hold it steady at that point. So not constant speed of 0. Trying to hold it steady at that point. And so our resultant force is 0. So we do have information about our resultant force because we know we're in equilibrium. So we know there is none. So we know that all of our x values and all of our y values should sum to 0, 0. Free body diagram. So up until this point, we've seen all of our forces pretty much. So point A, we're used to seeing, so for this, we're used to seeing everything except for this FD, right? We're used to seeing anywhere there's a line, we're introducing a force. However, there are invisible forces, I'll call them. So our force of drag, our force of gravity. We did have gravity in this one, but they had that line going to it, so it kind of still didn't seem invisible. But yeah, our force of drag. We can calculate A and B using the proportions here. That would be one method of solving it. The other method would be to do a proportion of, so if we know doing a proportion of the length to force. We'll go into that next week, I think. So for now, let's do the trig to find those values. Okay. In vector form, the equilibrium condition requires that the resultant force be 0. So this equation here is a resultant force. Make sure all those boxes are vector signs. Equals the tension from AB plus the tension from AC plus the tension from AE plus the force of drag. So then we can break them all up into their components. So our first one, TAC, I got angle beta. And then, oh my goodness. Angle beta, and then we can use our trig. It's a little skewed, but we can use our trig to find the x and y values of these. So what I'm doing here in these examples are doing trig, doing the like, so you know, I was saying you can either be consistent about always having your angle be from the x-axis, or you can do trig. So these examples are doing trig given the angles we were given. Another option would be to just use the angle that's, so like if we wanted to get TAC, we could do 90 minus this 20 to get this angle, and then we could just use our F equals cosine, Y equals sine equations. Does that make sense? Okay, so as we figure out terms, we fill in things into our table. So our force of drag we know is completely in the y. Our force of AE is completely in the y direction. That was this one. Our force of drag is completely in the x direction, or the negative x direction. Let's see, what else do we have? So here is our table. So on our FY side, we have, let's go FY first, the 19.84 plus our TAC value, a portion of our TAC value. So this would be the sine of whatever that value was, minus our 60 from AE. Force of drag is 0 in this case for our y value, so that would equal 0. That will give us one unknown of TAC to solve for. And then with our x, we'll have TAC, so we can solve for the force of drag then. This is how it essentially works out. Okay, cool. Any questions up to this point? Let's take a look at your homeworks. So the first two questions I closed out already were graphical method. So we have two questions, graphical method. Then we have 1, 2, 3 trig questions and 3 XY component questions. We'll talk about it more when we get back into class. When we get back into class, but week 4 is going to be our first test, and it's going to be focused completely on this homework. There'll be 3 questions. I have to refresh myself on exactly what those questions are. I know there's a trig element, I know there's an XY component element, and I know there's a total of 3 questions, so I have to figure out what that missing one is. Okay, so let's actually start with an XY component method. Let's start with this one. Knowing that alpha is 35 degrees, determine the resultant of the 3 forces shown. Okay, so we have 3 forces, so we know we want to use our XY component method. Let's get X. Okay, so we have, these forces don't have names, so I'm just going to go straight in with magnitude. I'll put one before it though, just so I can label our resultant force. Okay, so we have I'm going to go left to right, a 200 Newton force, a 150 Newton force, and a 100 Newton force. We can also blow this up a little bit. Okay. So we know that determine the resultant of the 3 forces shown. So we want to get a resultant. Okay. I'm going to do, okay. I'm going to kind of break it up extra. Just so to try to be clear about what I mean with there's 2 different ways you could solve it. I think you guys follow, but who knows? So absolute angle is going to be our angle from the positive x-axis. Let's even put in before that a relative angle. Okay. So for our 200, it is 35 degrees below our negative y-axis. Does that make sense? 35 from our alpha degrees below our negative y-axis. Absolute angle would be from the positive, from 0 degrees, right? It's going to be 180 degrees for a half of a circle, plus that relative angle of 35. Okay, so 150 is going to be, let's do 100 because it's easier. 35 degrees below the, this should be negative x-axis, and this should be the positive x-axis. I misspoke or misnotated. Okay, and so then this one is going to be that 35 plus the 30. Common mistake here is to have this one be a 30-degree angle. And that's going to mess you up. So this one's going to be 65 degrees below the positive x. Okay. So for this one, let's do 360 minus 65 and 360 minus 35. Okay. Does this make sense the way I did it? Hoping so. Okay. So in wanting to get our x-axis or our fx, x component, and our fy component, if we use the absolute angles, we can just go in with our standard equations down here. Fx equals f, so f would be the magnitude, right? Times cosine of, and I don't know, I have a feeling Excel would be Excel might be set up for radians, so it may give us an odd number right now. If I were to drag this down to, it should drag down all the values. So we should get B3 cosine D3. Perfect. Okay. And then over here, we're going to do our Fy equals F, magnitude of F, times the sine of our absolute angle. And if I drag this down, let's hope it goes with us. Let's see if these numbers make sense as well. That's the other thing. Okay. One quick way to check to make sure that these make sense would be to do and make sure their magnitudes are equal. So if we were to do the square root of the sum of the squares, meaning the square root of the x component squared plus the y component squared, it should give us that same value as that magnitude in the beginning, and that's just a quick check to make sure I did it right. Okay, cool. Here's why I'm confused though. This value. That value doesn't seem right to me because it is a, this should be double negative, right? Negative x and a negative y, and then our 150 and our 100 should be positive. Let me grab the answers because I do have a feeling it's an issue of, what's it called? Or the arithmetic element of it, or the trig element of it. Okay. So do our straight things, or whatever we do. in this case, they're doing like if you were to configure a triangle, just pay attention. So kind of how we did it in these ones where we created all the little triangles. Right, and then figured out the trig based on each triangle. Okay. Fill in our table. So I'm gonna just do kind of a rough thing to get our answers. -57, -135, -144, -163. Should have done 64, whatever. And 6, oh no, and 63. Okay. So then our resultant is going to be the sum of these columns. So our resultant in the x direction is going to be the sum of those. Our resultant in the y direction is going to be the sum of those. And then to find the magnitude of, so in this case, this is a good example of having two negative values. So we know our resultant is going to be in that third quadrant. Magnitude of the resultant force is going to be the square root of the sum of the squares. My values are going to be just a tiny bit off, maybe a little more than a tiny bit off, but and then when we go in with our tangent, we'd be getting the angle from the negative x-axis. So make sure you account for that. So in this case, our tangent gives us 86 degrees. But 86 degrees, we know that would be in quadrant 1. So we have to adjust for, well, we don't have to adjust. You can draw something like this and have just the answer 86 degrees. A little thing like that. Or you can figure out the absolute angle of that. Are there any questions on this? Okay. Are there any questions in general? I am starting to fade a little bit.
I just have a quick question. Could you reiterate why we had to find the absolute angle in this problem?
So it's up to you. So there's two ways that you could solve it. One is using a relative angle and creating like the triangles for each, kind of logicking out the trig. The other option is to do the absolute angles with, so if you were to do, okay, so if you're doing the absolute angles, you can just go in with, where did they go? Our cosine and sine equation. These ones. If you are doing absolute equation or absolute angles, you can just use these equations, the f of x and the f of y. Still have to be cautious with the tangent though. So that's one option. The other option is like using the stuff that we did from week 1. This is an old version, so it may be a little off from what you guys have, but using this kind of, so like physically making a triangle out of every one and then figuring out the, do you know what I mean? Does that make sense?
Yeah, that makes sense.
That's perfect.
But when we were doing like finding the fx and the fy with the cosines, didn't we use the relative angles, or was that?
So you will for some. So like in, so like anything in the first quadrant, it's going to be the same. Sometimes it does end up being the same too. I'm just not good with my what ends up being the same and what doesn't. Sometimes you'll have to switch what is sine and cosine. So if we were to have that one where we had the angle, the 20 degrees from the y-axis, or even like this one, you have like this 2 degrees here. Your sine and cosine functions would actually flip, and they would give you an opposite function, right? So like your sine would end up giving you your x value, and your cosine would end up giving you your y value. So there's ways to do it with the relative angle.
Okay, gotcha. Thank you.
Anything else? Okay. So that's all for me. The only other thing is actually not for you guys. I didn't make it to my Wednesday class. I didn't even get the virtual thing. So just for the Wednesday folks, I did upload the homework finally. Okay. All right. Anything else? I'll be on for a minute or two just in case there's any more questions. But thanks, guys, and thanks for your patience this week. We'll be back to normal soon.